Recording is rolling. It is Tuesday, December 6th, and I have an exciting lab lined up for you guys today. So, you guys see this PVC pipe T-shaped around here? So this is free to rotate. So there's a little bit of friction, but we'll worry about that close to the end. It's I'm gonna check this a whole lot. So you guys see this can rotate about the central axis. Ooh, I've got this red string. You guys see that red string right there, wound around. Okay, I'm gonna pull it through a pulley, hang a lab weight from it. Okay, and then as this lab weight falls, it's going to cause this to rotate. Now, do you guys think that this lab weight falling is going to accelerate as it's falling, like speed up as it's falling? Yeah, I think it would, right? There'd be a net force on it. It might be a small net force, right? It's weight down and the tension up, right? But they won't quite cancel out. So there'd be a small net force. So it's going to accelerate. Hey, if this is accelerating down, like accelerating in a linear sense, do you think that's going to cause this to speed up spinning, like have an angular acceleration? Do you guys think? Right? And what if I took these pipe arms off? I can do that. I can pop these out. Look at that. Okay. Do you think this is really easy to rotate? And then so it's easy to get going. And then once it is going, it's really easy to stop too, right? But what if I throw these arms back on? Pop those back in place. Okay. Now I definitely feel some resistance, right? It takes some effort to get going. And once it is going, it also takes some effort to slow it to a stop too, right? Oh, that means that this right here, in a rotational sense, has rotational what? Inertia. Do you think we can quantify how much rotational inertia this thing has? Okay. Maybe in some kilogram meter squared. Okay. So that's our goal today, is to figure out, well, how much rotational inertia does this have? That's what rotational inertia lab. Okay. That's gonna be the goal of this. So you guys have this half page on your desk. Everybody got one of these? You guys write your name on this? You guys write your name right here? Okay. So on one side is a table of values. I'll take you guys through the table and we'll go along throughout class. This is going to be a guided lab, so I'll do the whole thing up here. I do have to have somebody with a stopwatch. Who wants to volunteer for stopwatch duty? All right. So yes, you guys got. So you're just going to take a times for us. Okay. Then on the back side of this paper, we're going to look at a little bit towards the end, right? So we know exactly where this is going. You guys see a graph says torque versus angular acceleration. That's tau versus alpha. Okay. So we're going to make this type graph, right? And somehow we're going to extract this from it. I equals something, right? Rotational inertia. Okay. So again, keep this kind of big picture. The setup looks like this lab mass is providing a weight, which is providing a tension. I bet the tension is pretty close to the weight. It might be a shade less, right? Because this downward accelerator type elevator type situation. Okay? But that tension in the string is going to provide a torque, isn't it? Isn't this radial arm, the radius of the central axis crossed with this tension is creating a force? Okay? Isn't that kind of like this right here? Torque equals R cross F. Okay, that's a really small radius. It's probably about a centimeter. Actually, it's 1.1 centimeters is the radius, right? 2.2 centimeters is the diameter of that central pipe. Okay, so we have a radius. Okay? We're gonna have a force, which is this tension in the string, which is probably pretty close to the weight. Okay, and that'll give you a torque. But remember, the torque is also equal to this expression. Okay? Rotational inertia times the angular acceleration. Right? You guys see how this is all going to be connected? So that at the end steps, right, those will be the last few steps we do. We do this torque in Newton meters versus this angular acceleration in radians per second squared. Okay. What do you guys think this graph is going to look like? What shape do you think it's going to be? Give you guys a hint. If it's one pipe system with one rotational inertia, whatever that is, there's only one rotational inertia. The relationship between these two guys, does this look like y equals mx? Y equals mx? Huh. Okay. So what do you think this? Do you think it's going to be a linear type graph? Okay. The slope. Wouldn't the slope tell you what the rotational inertia is going to be? Okay. So we're going to get a bunch of data over the course of class today, and the slope of this graph should be the answer to this question, right? And we can quantify that in kilogram meter squared. That's why we're going to quantify rotational inertia. Okay. But before I grab any of that data, I want to get another perspective on this too, because you know what this looks a lot like, maybe not exactly, but pretty close to, is this right here. You guys remember if you have a rod rotating about its central axis, or about the center right here, that the rotational inertia should be 1/12 ml squared. I bet we can use this as sort of like a lower bound. We could here. Do you guys think if we ignore the central pipe, because the central pipe might be providing a little bit of rotational inertia, but not very much compared to this T-bar, right? Compared to these arms going out. Okay, so let's get an estimate, like a rough estimate, like a lower bound estimate using this, and then we'll get all the experimental data and we'll see how close it is to that. So, tell you guys, I measured this before class. I'll do it with you guys here. So 1/12 ml squared, right? Let's try this. So actually, you know what I want to do too? Here. I think this is probably going to be our official recording I'm going to use for most of my classes. So I'm going to break out one where you guys can see both sides on the same paper one right here. Okay. So before we ever do the official lab we're doing, let's say I is approximately equal to 1/12 ml squared for the scenario. Okay. So it's 1/12. Okay. Now what's the mass? The mass I got for each arm was 143 grams. So I'd have to double that and also turn that into kilograms. So what's 143 times 2 and then divided by 1,000 to turn to kilograms? Is that 0.286 kilograms for the mass? Okay. And then the length, here, got a meter stick right here. Okay. Now the full crossbar is more than a meter, but if I just measure one arm, I'm getting like 63 centimeters for an arm, 63 centimeters. Okay. So where's the picture go? Okay. So if this from here to here is 63 centimeters, then would the whole thing be 126 centimeters? Right, 126 centimeters. Okay. And then to turn that into meters, so I have everything in base SI units, is that called 1.26 meters? Okay. And that value is being squared. Okay. 1/12 ml squared, right? Okay. So put it all together. What's 1/12 times the mass in kilograms times 1.26 meters long being squared? Okay. Should be 0.038 around it too, kilogram meter squared. Okay. And remember, I'm calling this sort of like a lower bound estimate. So I bet the answer is going to be pretty close to this, but maybe a little bit more, maybe 0.04, 0.05, 0.06, somewhere in there, kilogram meter squared. You guys think? Okay. So that's what we should be looking for. But we're going to get this using but set this whole thing in motion. Right? You guys ready to do that? Set this thing in motion. Okay. All right. Let's take a look at this table. Right. Let me zoom in here. See what we got. Because some of these columns we're going to measure, and some of these we're going to calculate. The first four we're going to measure. So the first one says radius. What's the radius of the central axis? Now I measured ahead of time. I got 1.1 centimeters. Could you guys call that 0.011 meters? That's what that would be in terms of meters, right? We're going to do everything in base SI units today. Everything's going to be kilograms, meters, and seconds. Okay, so well, small values, but that big. So that's 1.1 centimeters radius. Okay. The mass, now this mass refers to the lab weight that I'm putting on it. So that's going to be our independent variable. So I'll save that, come back to that. The falling distance in meters, I'm going to let it fall 75 centimeters. That's what I've been using today. So guys, 75 centimeters, how many meters is that? 0.75. 0.75, right? Base SI units, right? Okay. And then practice is going to tell us how many seconds it takes to fall that distance. Okay. And that'll be all the measured values. That's it. Okay. Then we'll do some calculations, which are these four columns. But let's get the rest of these measurements first, and then we'll flip over that. I'm going to start with the big one, which is 1 kilogram. So isn't that your biggest lab weight? This one has a mass of 1 kilogram. So let's go 1.0 kilograms. Okay. I'll put the big guy on here. Okay. Now, so this is the biggest one that we're using today. Let me zoom out so you guys can see the picture too. Okay. So this is the biggest lab weight that we're using today. Is this trial going to run really fast or really slow compared to the other trials? Yeah, it should be really fast, right? It's got the most weight. It's going to provide the most force, the most torque. It's really going to get this thing going. Where's my? Here we go. I'm going to prop up the meter stick here so you guys can see this is falling about 75 centimeters. 0.75 meters. From there. All right, loop this through this pulley. hook this 1 kilogram guy right here. Okay, I'm going to start it from rest. It's going to fall some distance at some amount of time. Sounds like 3 kinematic values, right? Which is going to send us on a calculation quest. We wind this up, make this thing follow the proper height. Ooh, all right, I can feel it pull it. All right, you ready? Okay, okay, and get this. Okay, and go.
Oh, I messed up.
Okay, all right, that's right. It's sometimes mess up too. I rewind this thing.
Once it hits the ground, I should stop, right?
Yeah, when it hits the ground. Yeah, full falling distance. Oops, pop this back in the groove. So up to that height. Ooh. All right, I think we are ready. All right, ready? And go. Stop. All right, how many seconds was that?
It's like 9 seconds and 10 milliseconds.
Okay, it was like 9.1
Yeah.
second?
Yeah,
All right. 9.1 seconds.
I got 8.8.
Oh, okay, you got 8.8. Okay, so 8.8, 9.1. Do it. If you're taking your own data, that's okay. If you want to average it, that's right. We're gonna go with the here. I have this is our official timekeeper, so we're just gonna do that.
I thought it was 9.1.
Oh, sorry. Yeah, you're right. 9.1. Right. Yeah, thanks. Also, we're just gonna do one proper. I know I have like 3 set up, like 3, 3, 3, 3, 3. We're just gonna do 1, 1, 1, 1, and 1, just to fit this thing last time.
Sorry, I can't see your screen. Do you know what what's the radius? Okay.
Let's get that. Okay, so that's all the measured values. Okay. Now let's do some calculations. Now this one here, what are these things? We got linear acceleration, we got tension, we got angular acceleration, and we got torque. Right. So linear acceleration. Ooh, do you guys remember that story when Paul Hewitt walked into a mine shaft and spread the traffic? How deep is it? Drop a rock, 5 seconds, about 125 meters deep. College, you guys remember that? Okay. Wasn't that this right here? X equals 1/2 AT squared. Some version of that, right? Now they were using pure free fall, fell for 5 seconds, so it must have been about 125 meters. Okay. But we don't have pure free fall. Actually, we want to know what this acceleration is, given everything else. This is starting from rest, isn't it? Starting from rest. Switch its headset. Okay. All right, so starting from rest, fall from distance for some amount of time at 3 kinematic values, so we can't solve for this. Can you shuffle up this 2? 2x equals a t squared. Divide the t squared down. So acceleration is 2 times the falling distance divided by the time of fall squared. That's what that is, right? Right? Which is exactly what this does right here. 2x divided by t squared. That's where it comes from. So let's pull up calculator. Do 2 times the 0.75 meters falling distance. Zoom out here a little bit. So 2 times that x divided by the 9.1 seconds squared. And that is 0.018. So 0.018. That's meters per second squared. That's a tiny, tiny acceleration, isn't it? Okay. The next column says tension is, okay, now this is something we've derived before. Actually, let's sort of have it here for my AP kids. Okay. Do you guys remember this? Net force is mass times acceleration. That's due to second law motion. The net force, wouldn't that be the weight down and the tension up? And you have to take the difference between those two, like free body diagram, the weight down and tension up, right? Which would be really small difference, but that would be equal to mass times acceleration of the thing falling. Now, if you rearrange that and solve for tension, isn't that m times g minus a, right? That's a scenario for an elevator accelerating down. Right? That's a poster hanging on my ceiling right above that wrench in the back. If you want to see that, that's also basically the same thing, just derived. Okay. Now, if I write that down, okay, I'll do F sub T, the tension force, because capital T is used for other things too. Okay. Is m times g minus a for a downward accelerating elevator, which is what we have. We have a mass of 1 kilogram, so 1.00 kilograms. Okay. I'm going to use a precise value today for G. I'm going to use 9.8 meters per second squared. Okay. And the acceleration, like the physical acceleration, well, we just calculated that. Isn't that 0.018 meters per second squared? Right? Is that true? But look at this right here. What is 9.8 minus 0.018? Isn't that basically 9.8? I mean, it's a shade less than that, but right. So could I basically ignore this A part and say the tension's just really close to 9.8 newtons? It's really like 9.78 newtons, 9.78 newtons, but 9.78 compared to 9.8. I mean, that's a rounding error that is even less than we usually just round this to 10 newtons anyway, right? Right, you guys see that? So what I'm trying to get at is that if you want to be strictly true about this, you really have to use the elevator formula, but this A is so small compared to this G that probably for the rest of this lab, I'm just going to round this to N times G. Okay, so I'm going to call the weight, I'm going to call the tension equal to the weight, which is 9.8 newtons, because the difference is like a rounding error. Okay, you guys kind of got that? Okay, and that's especially true for the smaller lab weights too. Okay. All right, next one, torque. Or sorry, whoops, angular acceleration. Oh, do you guys remember how you go from linear acceleration to angular acceleration? That's this guy right here, isn't it? Okay. All right, so we know what linear acceleration, it's a really small value. That's your 0.018 meters per second squared. And we know the radial size, that's your 0.011 meters. So can you divide that over and solve for alpha? That's what that would be, right? Isn't it? Got that, got that. Okay. If A is equal to alpha times R, then isn't alpha just equal to A divided by R? Right? Okay. Which is exactly what that does to do. So we're going to take this acceleration, the 0.018 meters per second squared, divide by 0.011 meters radius. I'm getting 1.65 radians per second squared. Is that what you guys are getting to? Pretty close to? Okay. Again, if you used your own time calculation, you might have the number slightly different than that, but it should be pretty close to that. If I did the calculations right. It's radians per second squared for this thing speeding up spinning is what it's telling you. Okay? And the last column, torque. Now, you guys know torque is R cross F, and the F in this case is the tension force, which again, we kind of rounded to just being lab weight. Okay, I'm going back to this, right? Torque is R cross F. Okay. So we know the radial size, that's a little over a centimeter. We know the force, the tension in the string, pretty close to lab weight. So let's just cross those. So what is 0.011 meter radius crossed with a 9.8 Newton force? It's 9.78, but I'm just gonna call it 9.8. Okay. Okay. 108 about. I keep 3 digits. Okay. And that's Newton meters of torque. I think that should be the biggest torque value that we have all day today. So, okay. You guys got that? Okay. All right. And what I'm going to do here on out is I'm just going to switch out this 1 kilogram lab mass with different lab masses. Right? And then we're just going to repeat that process. Get a few measure values. Those are your measure values. Get some calculated values. Okay? Now, the radius is the same all the way down, so I could just copy paste the radius all the way down, right? That's not going to change that many meters, right? So is the following distance. Okay. We're just going to do 1 trial for each of these, although it is good practice to do like 3 and take an average, but only got so much class time, so it's going to do that. And then, all right, let's go. How about 500 grams? Isn't that called 0.5 kilograms? Right? Which also weighs about 5 newtons. We're going to say 4.9 newtons, a little more precise. So we've got 0.5 kilograms right here. I'm going to hook this guy on and set this thing into motion. There. Oops. It fix the string. All right, there we go. All right, practice ready. Go down. All right, ready? And
Wait,
oh, okay. All right, I got it.
all right, yeah,
And go. Stop. How long was that?
it was 14.56.
14.56. All right. 14.56 seconds. Ooh, took a little longer, right? Yes. Okay, so the time was 14.56 seconds. Okay. Hey, look at that. We have half the mass, therefore half the weight, about half the tension. Okay. But ooh, did the time go up by about square root of 2 is about? That's 9.1 times the square root of 2, I think. Pretty close to, right? Something like that. Right, acceleration, 2x divided by t squared. So let's do 2 times the falling distance of 0.75 meters, divided by the time, 14.56 being squared. And that is 0.0071. 0.0071. That's meters per second squared. I'm going to skip a column and just get the angular acceleration right here, because I can just divide this by the 0.011 meter radius. So that's 0.64 radians per second squared. Okay. Let me go back and get the tension. The tension is just going to be the lab mass times 9.8 meters per second squared. Okay. I'll call it 4.9 newtons. Now you guys know it's a tiny, tiny bit less than that, but we're just going to round it up. And then torque, R cross F. Let's take this radius of 0.011 meters and cross it with the tension force of 4.9 newtons about. I'm getting 0.054 Newton meters of torque. All right, good to go. All right, next one. Oh yeah.
I was wondering, is there such thing like on Earth as like a perfect vacuum?
Perfect vacuum. Oh, well, even if you're talking about like yeah, if you're talking about like getting rid of every single atom of air, ooh, I think even if you go down to like deep space, there's like, you know, like a couple of hydrogen atoms per cubic meter. So yeah, it's hard to get like a perfect vacuum, but maybe like for practical purposes.
It's like a vacuum where like an anvil would fall and fast like a feather.
Yeah, you can do that. Yeah, you know, actually after this lab, I have a few spare minutes. I can pull the video, pretty much exactly that going on. Yeah. So remind me of that. And we'll do that too. Okay. I'm gonna bump this down to like 0.30 kilograms. What I'll do is I'm gonna combine. Where is it? Here we go. I'm gonna tag on these two right here. 200 grams and 100 grams. So it's 300 grams. I'll call it 0.30 kilograms. Right. So that's gonna be our next trial. Tag both these guys on. So the mass is getting less and less, therefore the weight and the tension and the torque is getting a little bit less. So it should take a little bit more time to reach the ground. All right, ready? All right, and go. Ooh. All right. So it is moving. It is even accelerating. It's really subtle. It's speeding up at a slow rate. All right, and stop. All right, how much time?
20.93.
24.93.
No, 20.93.
Oh, 20.93. All right, 20.93 seconds. Rewind this thing. so 20.93 seconds. Right? So the linear acceleration, so 2 times the falling distance of 0.75 meters divided by 20.93 seconds being squared. And that is, here, I'm gonna do this kind of sideways, 0.0034 meters per second squared, tiny, tiny acceleration, right? But it had to have been accelerating because it started from rest and it was moving and even speeding up a little bit. The tension, again, I'm going to round those, call it 0.3 times 9.8. Okay, so it's a tiny, tiny bit of an overestimate, but 2.94 newtons of tension. Okay, and then angular acceleration. Whoops, I should have done started. Okay, so go back to my linear acceleration, and I'm just going to divide by the 0.011 meters of radius. That gives you 0.311 radians per second squared. Speeding up spinning. Okay. The torque, you take this R, cross it with this F. 0.011 meters radius, 2.94 newtons of force, 0.0323, about 0.032 with that. That'd be Newton meters of torque, if that costs that. All right, let's go 0.20 kilograms. So I'm just gonna put on the 200 grammer, 200 grams. All right, got 200 grams right here. All right. All right, ready? And go. Stop. All right, how much time?
Is 31.74.
31.74. All right. Okay, 31.74 seconds. Okay. So acceleration, linear acceleration, go 2 times the falling distance divided by the time being squared. And all right, so no, it's really tiny, 0.00149. I'll call it 0015. How about that? And then the tension, let's call it 0.2 kilograms times 9.8 meters per second squared, get about 1.96 newtons of tension. Okay. Let's take that linear acceleration divided by 0.011 meter radius. That's 0.135 radians per second squared angular acceleration. And finally, let's do 0.011 meters radius crossed with a 1.96 newtons of force. Get 0.022 Newton meters of torque. All right, let's go one last trial. I'm going to put 0.15 kilograms on there, and I'm going to get that by combining the 100 grams and the 50 grams. Okay? I tried to just do 100 grams earlier, but see, there is a little bit of friction with this pipe system, and this was like right at the tipping point. So 100 grams just not quite going to do it. But these two guys together is going to pull us probably about as slow so we can get this to still work. Okay. All right, so here's 150 grams. Oops. Ooh. Just a little bit. All right, very fresh. And go. Stop. All right, how much time?
43.99.
43.99 seconds. 43.99 seconds. Yay. Alright. 43.99 seconds. Okay. So 2 times the falling distance divided by the time squared is 0.0078 meters per second squared. The tension, take the mass times gravity, get 1.47 newtons of tension. Let's go back to that linear acceleration divided by the radial size, get angular acceleration of 0.070 radians per second squared. And the torque is R cross F, which is 0.016 Newton meters of torque. There you go. So we've got 5 points. Okay. Now on the back of your guys' paper, but let's go on the right side here. Let's keep this all on one screen. Okay. You guys see there's torque in Newton meters versus angular acceleration and radians per second squared. Okay, that's what those axes are labeled. Okay. And I know we talked so at the top of the class, but torque is R cross F. That's what we did experimentally. And this is what we're going to graph, torque versus alpha. So that the slope of that line, it should be a straight line, and the slope should be equal to what we're looking for, the rotational inertia of this pipe system. Again, it's hopefully close to this number, but we're gonna find out. So alpha, it looks like my largest alpha is 1.65 radians per second squared. So let's go about 0.5, 1, 1.5, 2. Okay, so you guys have scaled this with me? 0, 0.5, 1.0, 1.5, 2.0 radians per second squared. And how about the torques? The largest torque was 0.108 Newton meters. So about 25, 50, 75, 100. Okay, let's go 0, 0.025, 0.050, 0.075, and 0.10. Okay. And then the biggest torque is just a shade above that, right? But it'll still fit right here. Okay. All right, so let's plot these like XY coordinates, like XY, except it's alpha torque. Okay. So 1.65 radians per second squared is about this much torque. There's a point right about there, pretty close to it. Okay. Then 0.64 meter, so what, no, 0.0. What did I just? Okay, yeah, 0.64. All right, I think we got 0.64 radians per second squared corresponds to 0.054. It's right about there. Okay. Newton meter support. 0.311 radians per second squared is 0.032 Newton meters of torque. 0.135 radians per second squared is 0.022 Newton meters of torque, and 0.07 radians per second squared is 0.016 Newton meters of torque. It's pretty close to a straight line, doesn't it? Close straight line. Let's here. Here's what my first period class got. That's my, and then here's what my last class got. And these guys right here, look, they're all like straight lines, right? Like that. But what you'll notice all day today that there's been a y-intercept. You guys see that this actually misses the origin. It goes up a little bit, right? Same thing here. Yeah.
Is it because of friction?
Boom. Yeah, exactly. This is frictional torque right here, isn't it? So we have y equals mx plus b, where the slope represents rotational inertia, and you're right, the intercept represents frictional torque. Okay? Because for 0 radians per second squared, there had been a little, there's like minimum lab weight. Remember I was telling you guys 100 grams, it's like right at that tipping point. Okay. So let's do rise over run and get the slope of this line. So the rise is here. I'm just going to go from the biggest point to the smallest point and just take the straight line between those two. Okay. So the change in torque. Okay. We're gonna draw this out. We're good today. Got a change in torque per change in angular acceleration. Okay. Torque equals I alpha A plus frictional torque. Y equals mx plus b. And so the change in torque is 0.108 Newton meters minus 0.016 Newton meters, which is 0.092 Newton meters of torque. Okay. And the change in angular acceleration is 1.65 minus 0.07 is 1.58 radians per second squared. Okay. So if you do rise over run, it's going to be this rise per this run. What is 0.092 Newton meters divided by 1.58 radians per second squared. Okay. Now, before I hit enter, what am I hoping this number is going to be pretty close to again? Remember before we ever started this thing, we did 1/12 mr squared or ml squared. We were doing this geometry perspective right here. We said it should be kind of, but we were saying this is probably like a lower bound estimate. So it's probably a little bit bigger than this, but hopefully not too much bigger. Should be pretty close, right? Okay. Moment of truth. We're going to find out. 0.058 kilogram meter squared. Look at that. This is about 0.4, it's about 0.6. So what we got is about 50% bigger. Actually, we can get it exactly, right? What is 58 compared to 38? Yeah, about 50% bigger, 53% bigger than what we had estimated as lower bound estimate. So yeah, that looks good. Looks good right there. Okay. So once you guys got all the data, you guys got the graph, you guys got the answer right there, then make sure your name's on your paper. Pop that in the grade tray. That's what we got today. Yeah, we do have a few minutes. I'm going to find a feather falling in a vacuum for you guys too.